Ever wonder what really makes a game tick? Beyond the slick graphics and the cool story, there's this invisible engine running the whole show. An engine made of pure logic and rules. Today, we're going to pop the hood and take a look at that engine, the unseen architecture of play. We're talking about core game mechanics.
And before we dive into all the technical stuff, this question from the playwright Molière is the perfect place to start. Because at the end of the day, all the complex algorithms and systems we're about to break down, they all have one job: to create an experience that's engaging, satisfying, and just plain fun. It's a great lens to look through for everything that follows.
So here's our game plan. First, we'll nail down what core mechanics actually are. Then we'll get into the 5 basic types you see everywhere. We're going to do a deep dive into game economies, see how mechanics guide you, the player, then look at how these ideas become actual code, and we'll wrap it all up with the fascinating world of randomness in games.
Okay, so what are core mechanics? Well, think of them as the bridge between a designer's cool, abstract ideas and the cold, hard rules that a computer can actually understand and run. It's all about turning those vague concepts into super precise algorithms.
This right here is the perfect example. On the left, you've got this hazy idea, penalized for taking too long. Okay, but what does that mean? You can't code that. But look at the right. That is a precise mechanic. You've got data, 1 inch, 3 seconds, 3 minutes, and you have a clear algorithm. That is something you can build a game with. It's that jump in specificity that creates real gameplay. And that brings us to our formal definition. Core mechanics aren't just the rules in the instruction booklet. They are the whole shebang, all the data and all the algorithms that work together to generate the gameplay experience. They are, quite literally, the heart of the game. Now, designers aren't just pulling these mechanics out of thin air every single time. Most of the systems you see in games can actually be sorted into one of 5 major categories. You can think of it as a kind of classification system, a taxonomy, for understanding how games work under the hood. So here they are, the big 5. First, you've got physics. That's all about motion and force, right? How high your character jumps, how a grenade bounces. Then you have internal economies, which is huge. It handles any resource you can count, like gold, ammo, or health. Third is progression, the mechanics that move you through a story, like a key for a locked door. Fourth, tactical maneuvering. Think chess, controlling pieces on a board. And last, social interaction, the rules that manage how players team up or betray each other. Now, of all of these, internal economies are by far the most common, so we're going to zoom right in on those. Almost every game you've ever played has some kind of internal economy. It's a system that controls how virtual resources are made, used up, and traded. And remember, we're not just talking about money here. Health points, magic, ammunition, even the enemies that spawn. That can all be part of a game's economy. Any game economy, no matter how complex it seems, is built from just a few simple parts. You've got a source, which is like a tap that creates resources. Think of an enemy spawn point. You've got a drain, which uses them up, like firing your weapon uses ammo. A converter, which, you guessed it, turns one thing into another. And a trader, which lets you exchange stuff. These are the basic building blocks for everything. But what happens when that flow of resources just stops? Well, that's a nightmare scenario for a game designer called a deadlock. It's when the whole economy just grinds to a halt. The classic strategy game, The Settlers III, actually gives us a fantastic real-world case study of this. Okay, check this out. It's a classic catch-22. You need stone to build the hut. But the hut is what produces the stone. So what happens if you spend all your starting stone on other buildings? You're stuck. You're in a deadlock. You can't build the hut, so you can't get more stone. Game over, right? Well, the designers were clever. They saw this coming, and they built in a solution. They let you demolish other buildings to get a little bit of stone back, just enough to break that loop and get the economy moving again. That's what smart design is all about. Mechanics aren't just for managing numbers, though. They're also what shape your entire experience as a player. And usually, this comes down to a balance between 2 big ideas: progression, which is kind of like a guided tour in a story-driven game, and emergence, where amazing gameplay just naturally bubbles up from a simple set of rules. So in games that are all about progression, designers have this whole toolkit to make sure you stay on the right path. They're the ones making sure you see the story beats in the correct order. We're talking locked doors, one-way passages, secret areas. All these little tricks are carefully designed to manage your journey through the game's world and its story. And then you've got the total opposite, the goals in tactical games. Here, the designer just gives you an open space and a set of rules, and the actual gameplay, the strategy, emerges from how you decide to play.
The goal isn't to follow a preset path, it's to achieve an objective, like controlling a choke point or wiping out the other team. It's about gaining an advantage, not following a sequence. So, with all these ideas floating around, how does a designer communicate this stuff so a programmer can actually build it? Well, they have to get super specific. They have to define the game's fundamental building blocks in a way that translates those abstract ideas into data that a machine can actually track and manipulate.
And this right here is an absolutely critical distinction they have to make. A resource is the general idea, the type of thing, like the concept of marbles as a commodity. But an entity, that's a specific individual instance that the game has to track. It's the actual 15 marbles sitting in your character's pocket. You have to get this right because programmers need to know exactly what entities to create and what resources they represent. Which leads us to this golden rule of game design. The designer's job is to specify what the game needs to do. The rules, the mechanics, the feel. The programmer's job is to figure out how to make the computer do it efficiently. The designer is the architect. They design the game, not the software itself. All right, for our last section, let's talk about something that feels like the complete opposite of precise rules: chance. Randomness is an incredibly powerful tool for a game designer, but as you're about to see, it is rarely ever as random as you might think. See, games almost never use truly random numbers. They use what are called pseudo-random numbers. They're generated by a fancy math formula that starts with an initial number called a seed. And here's the trick. If you use the same seed, you get the exact same sequence of random numbers every single time. And that's not a bug, it's a feature. It makes testing and balancing the game predictable and, frankly, possible. But how you use these numbers makes all the difference. If you roll a single die, you get what's called a uniform distribution. Every side, 1 through 6, has the exact same chance of coming up. But watch what happens on the right. If you roll 3 dice and add them up, the odds are not equal anymore. The results start to clump together in the middle. You get a bell curve. This chart shows that bell curve perfectly. Think about it. There is only one possible combination to roll a 3, a 1, and a 1. Same for an 18. But for a 10 or an 11, there are 27 different ways the dice can land to give you that total. That means a designer knows you are literally 27 times more likely to get a result in the middle than at the extreme ends. And that is an unbelievably powerful tool for balancing a game. Which leaves us with this final thought to chew on. In a world that is built from the ground up on precise deterministic rules, what is the role of chance? Is randomness a bug that undermines all that careful logic? Or is it the essential feature that makes a game surprising, replayable, and, ultimately, a true pleasure to experience?